And so I will start out with roughly half an hour about electrostatic solvers and what are they good for and how do they work and what do you have sometimes to watch out for. Because electrostatics under periodic boundary conditions is one of the more complicated things in molecular dynamics. And so you have to take care in a special way. And I will walk you a little bit through. Okay, so the overview is I will talk a little bit about the problem, then introduce the main workhorse, which was the Ewald summation, so which is called the standard Ewald, because there's a more advanced one, which is the particle mesh one. Then I will talk about a library which you can use within ESPResSo, which contains a lot of electrostatic algorithms. I mean, this is not really, let's say, for the day-to-day work, but if you're interested in playing around with some other routines, and there are a bunch of other ones included. Then we will talk about confinement. So this runs under the name partially periodic geometries. And I will show you how to deal with dielectric interfaces and what constant potential methods are good for. The electrostatics is long range. So in principle, we cannot use the tricks of the trade we are normally used to in molecular dynamics. I mean, remember, MD is a popular method which scales like n with a number of particles, but just because we're using tricks like cell decomposition, which renders the problem of n squared, because you have to compute the forces between particles. So it's a pair interaction, so it makes it n squared, down to linear scaling, because you can use cell lists, and those require that there is a short range cutoff for the interactions, and Coulomb certainly is not short range because it's 1/r, so it's long range. We cannot simply use a cutoff scheme, or in principle you can, but then you introduce artifacts, and this is not what you want to do. So the general idea is, of course, I mean, if it's long range, you make a pair energy summation of the interactions, like it's shown here in this formula. What a popular length scale in electrostatics is the so-called Bjerrum length, which is simply the interaction energy of the length scale at which two interactions have an interaction energy of kBt. And so if you reformulate the problem, you end up with this formula. So the Bjerrum length appears always as the electrostatic prefactor. It's proportional to the inverse temperature. And that makes the formulas just look nicer. So this is basically where you introduce your prefactor. And if you're interested, what's the Bjerrum length for water? So that is 7.1 angstrom. This is the usual way how mappings occur in a coarse-grained simulation. So as you see, it's pair. So it would be costly because it would go like n squared. And this is, of course, not nice. Now, in open boundaries, you have basically two ways of how you can compute the electrostatic energy. You can do it once over the pair, as I was writing up here on the left-hand side. So it's a pair energy summation, or you can say I do a potential summation and then I sum over every charge multiplied by the potential at the position where the charge is located. And where do I get the potential from? Well, I get it from solving Poisson equation. But if we are now in a periodic geometry, of course, you have to keep track of the boundary conditions. So in open boundary condition, this is completely equivalent because you just sum up what's there, you solve what's there, and these are equivalent. Now, under periodic boundary conditions, first is the question, how do you sum up the pairs in a periodic lattice crystal? Because that is what you will do when you use periodic boundary conditions. You will just replicate the system infinitely. Then the standard way of doing is, or one of the standard ways, you say I do it in concentric shells, and this is how you will write it up then, saying I take the charges, how they appear from the central box. I will go in concentric rings and make them longer and longer, multiplied here by, I mean, denoted here by this radius, basically m squared. And then from the mathematics, because it's 1 over r, you get a conditionally convergent sum. And a conditionally convergence, just to remind you, is that the sum, that the summation order is important. So conditionally convergent sums are always kind of cumbersome because you can get any result you like, just depending on how you sum up the terms in the sum, and therefore the notation of how you did it is very important, because if somebody else would like to compare your result with the one you obtained, if you use the different summation order, he gets a different number. That doesn't mean that you did both something wrong. It's just you didn't communicate well enough what's the summation order. Now, on the other side, if I do it via potential summation, I have to solve Poisson's equation imposing periodic boundary conditions. So then you get, because you do it on the torus. I mean, this is basically what periodic boundary conditions mean in 3D. You have a 3D torus. You get a periodicity in U, but if you do it in this way, U is not periodic. So these two things are in principle different, and the difference is actually the so-called dipole term. I mean, people have figured that out using lattice sums, that there is another term which you have to add in order to make these two results convergent. And the dipole term in the standard lattice sum has this form of that is 1 over what's called the boundary condition at infinity. So the idea is you sum up charges where something at infinity might have the same or a different epsilon. So epsilon is the relative dielectric constant. And there has been the saying, well, if you use metallic boundary condition, then you assume that you're surrounded by metal. And that basically is the equivalence of saying that I'm solving the Poisson equation in the toroidal sphere, because that means that the electric field lines cannot go outside of your boundary, and this is therefore called metallic boundary conditions. And if you see under metallic boundary conditions, there's actually no need to talk about the dipole term, because epsilon is infinity and the dipole term goes away. Actually, metallic boundary conditions are the ones you should basically always use, because they're always safe. And then we wouldn't need all this discussion. But because in all the literature, you always see that there is this dipole term, and you might wonder, I mean, what happens if you use it or not? Please ignore it. But it will become important later, because there is some, and that relates back to the conditionally convergence of the Coulomb sum. The dipole term can do something good for you, because it specifies in a way the way you do the summation of this lattice sum. Now, before we come to that more intricate part, let's talk about the standard Ewald sum. It's related to the name by Paul Peter Ewald. He was actually here in Stuttgart for quite some time at the at that time still Technische Hochschule Stuttgart. And you might wonder, why did he worry about Ewald sum? Because computers were not yet invented at that time, but he was interested in the theory of X-ray crystallography, so how to compute interactions in periodic crystals, and those are also infinite dimensional objects with a certain periodicity. So this is exactly what we need in the MD simulations. So the calculating the Coulomb potential is difficulties on two sides, because it's of course singular at each particle positions, because it's 1 over r. So if you overlap, you run into infinity, and the tail is very slowly decaying. I mean, this is the reason for the conditional convergence, is also the reason why we cannot simply cut it off, because also things very far away can still contribute, especially if you then go to infinity. Now, the idea is to separate these two problems. First, to calculate the fast decaying short range part in real space. And why I'm talking about real space is because we will use some Fourier transformations in order to make this problem handle this problem. And on the second part, you will calculate the long distance part in Fourier space. Now, this is that you say, well, I would like to split the potential. If I just think in one-dimensional terms, and there's a unit charge maybe here, and there's a unit charge there, so it's singular, it's a delta function. What you do is you add Gaussians in order to smear out this charge and to smear out this charge. And if you add the Gaussians, I mean, you add them basically on the opposite, with the opposite sign, then you get basically this picture. You have a unit charge +1, you add a -1 smeared out Gaussian. So there's a little bit remaining, which you will later on calculate. But of course, because you added something, you have to subtract it in order not to distort the result. And that leads to this Gaussian part. And then the trick is via mathematically going into Fourier space, you can basically get analytical results for these kind of interactions. So the Gaussian which you has one parameter, which we will see later on more often. This is this width of the Gaussian which you add. And here mathematically you add it and you subtract it and you haven't done anything wrong. And then you go through the calculations. And at the end of the day, so there's a good, if you want to really follow this, you can look, for instance, in the book by Frankel and Smith. So they're really for the layman, then they calculate it out for you. Here's a dipole term, but you end up basically with these two parts, which are the real space part of the Ewald sum and the Fourier space of the Ewald sum. And if you look closely enough, there's an error function, the complementary error function appearing, which is an exponentially decaying function. And here you have the exponentially decaying function already in your face. They are both, one goes with alpha. So with the widths, one goes with 1 over alpha squared. So they are oppositely related. I mean, if you now turn your knob on alpha, either one gets big, the other gets small, or one gets small, the other one gets big. So there is some sort of trade-off which you have to do. We will talk about this in a second. But these are the main contributions: the real space part, the Fourier space part, and then there is a self-interaction term, which is basically constant, doesn't depend on R. So when you take the derivative in order to get the forces from here, the forces are that what we need for MD, it goes away. So basically you always deal with these two terms. Now the complexity can be shown to be reduced from order n squared, but where we started out, because it's Coulomb, n squared. But you can, via some judicious choice of alpha, you can reduce the complexity to n to the power 3 over 2. And so this was state of the art, let's say up to the end of the 80s, beginning of 90s. People have been always using Ewald sums. Even later, people still used Ewald sums, but it's very slow and not really state of the art. So what happens next? Well, actually, when I said end of 80s, this is when, let's say, my personal Bible came out, written by Hockney and Eastwood. They introduced a lot of things which you can use in order to speed up molecular dynamics. And in particular, they already laid out the foundation of what you have to do in order to speed up also the electrostatic algorithms. Because they always proposed the idea to using fast Fourier transformations. They came out of plasma physics, where I don't know, it was maybe more useful to do this. So the idea was actually in the near field, use the standard Ewald, in the far field, replace the Fourier space sum by a discrete fast Fourier transform on a regular mesh, and that brings down the computational order down to n log n. Now, this book was rather complicated to read in that time. Actually, the method of Hockney and Eastwood goes back to end of the 70s. So this is when they first started saying you can use fast Fourier transforms, make everything faster, but it's clearly spelled out here in this book. So the wheel got reinvented by Mr. Darden with the particle mesh Ewald. This is where it still gets its name from. Particle mesh Ewald is the mostly used convention that people talk about, but this method is really not good. So they came up 2 years later with another one, which is called the smooth particle mesh Ewald method, which in principle is as good as the Hockney and Eastwood method. They also invented some other things at that time. But I will show you in a few slides that this particle-particle-particle mesh, or P3M as it's still called, is still the best for a specific reason. So I can say it with Tina Turner, it's simply the best. And if you're interested, you can look here in these slides and this reference where we actually compared all three methods and showed what the differences are. Now, I walk you through very fast through the steps of the P3M. So the idea is you solve Poisson's equation here on a grid. The key thing, which will become key later, is that you solve Poisson's equation by multiplication here with what's called the optimal influence function. So it's that's the lattice version basically of the continuum Green's function, and it will be constructed in such a way that you actually minimize lattice artifacts. You can actually analytically show that there is a particular influence function which minimizes the lattice artifacts for either the energy or for the force or whatever observable you have in mind. And that basically tells you that you analytically have the optimal version. I mean, there's nothing which can beat it, because analytically you showed that this is the optimum. And therefore I say P3M is the gold standard, because you can't beat it. I mean, you can get very close, and SPM gets very close to it, but it's on the, you make it more complicated than it would have to be. Now, because you solve everything on the lattice, this is where the fast Fourier transforms live. You still use, of course, Fourier space differentiation, and you can transform the field back and forth. And at the end of the day, you obtain the forces. And this is more or less how a P3M works. There is another parameter now in the Ewald summation, which is basically the grid order which you're using, which comes from this charge assignment. Because the charge, of course, lives in free space. It can be anywhere. But now you have imposed that there is a grid on which you have to map the Coulomb charges. And you can do this in many different ways. So because of the analytic form, the particular nice analytic form, Hockney and Eastwood use so-called cardinal B-splines. This is, I mean, basically the same what SPME uses. And you can do that to any order you like. The higher the order, of course, the more costly it is, the more accurate it is. But there's, of course, a trade-off between costs and accuracy. And there's also an optimum. So there's another parameter which you have to optimize in order to get the fastest thing out of your assignment. I come back now to this optimal influence function, because you might wonder, how did they really construct it? And the way they construct it is saying that, let's suppose I know the analytical value of the field at the position I, and I have now my lattice version of the field. Then I would like to minimize this functional between the true reference world and my grid imposed one, and I can make a square out of it. I sum over the whole volume, and I solve all. I also average over all the positions in the grid where I'm supposed to be, because the artifacts might depend on where I am in my space. Because if I'm right on my lattice, on the lattice point, there's basically no lattice artifact. But if I'm somewhere else, there is something. And then the miracle more or less is that you make a variation. I mean, you make a variation trying to find the minimum, and you can do this analytically. And this leads to this optimal Green's function, or the optimal influence function in Hockney and Eastwood. Now, I always talked about error. I never told you why I think it's important to think about errors. Well, on a way that should be obvious, of course. You would like to have a value which is as close to the real value as possible. But it's a little bit like doing quantum mechanical calculations. I mean, to go to the exact value is too costly. It would take forever. And therefore, you say, I'm already happy if I reach a certain accuracy. Let it be 10 to the -4, 10 to the -5, whatever, relative accuracy in my forces. And I can say, this is my bound, which I would like to allow. And then I can ask, what kind of work do I have to do in order to achieve this bound? And now I told you in the standard Ewald sum, the only parameter we have, well, it's not the only one. I mean, we basically have 3 parameters. I mean, it's this alpha. Remember, alpha was the width of the Gaussian, which we added in the standard Ewald summation. And then we had these infinite sums, the real space sum, which you can sum up to infinity, and the Fourier space sum, which you also could sum up to infinity, which you of course don't want because they're both exponentially convergent. So you have to choose a cutoff. These cutoffs are called R and K max. So R max is the length over which I would allow to sum in real space. K max is my Fourier space cutoff. And depending on these values, I will get curves which show me the error as a function now of my fudge parameter alpha, the width of my Gaussian. And depending on how big this Gaussian is or how I choose it, I have either an increase in real space error or an increase in Fourier space error. And now these terms go here down exponentially, and you see there's a clear minimum here. And this is the optimal value of alpha, which you have to choose in order to make this the sum optimally converging. Because if it would stay here, I mean, the real space, the Fourier space error would be very small, but the real space would be high. Sorry. If you are somewhere here, then it's just the other way around. So choosing the optimal alpha is important because we are here on a log scale. So small changes make a big difference. And therefore, to hit always the right points in your parameter space is important. And the question is, how do you do this? Well, luckily enough, there are formulas which tell you exactly how the real space value varies with alpha, and there are formulas how the Fourier space error varies with alpha. So you can basically fit these 2 curves here, which go down there, and find always the optimal ones by using the intersection point. Now, these come from Colaffa and Peram. And for P3M, there's actually an equivalently easy error formula for the Fourier space, because the Fourier space is not now the continuous one, but the fast Fourier one. And it's of course more complicated because you have the lattice algorithm, but Hockney and Eastwood gave you basically a way to detect what the error is. And so one has very easy formulas where also the mesh order of the cardinal B-splines goes in. And this is actually what ESPResSo is using. We have internally all these equations, and we can find the optimal set of parameters which allow you for a predefined accuracy to set your parameters such that you are actually also optimal in speed, because computers may differ in how fast they can do fast Fourier transforms or real space and Fourier sums and so on. And you can test a bunch of parameters which give you the same accuracy and say, okay, this bunch of parameter is the best one, and then it runs fastest on your computer, on your chosen hardware. Now, this was all to general Fourier sums. Now the question is, what do you do in partially periodic systems? Because in slabs, for instance, slit pores, like you want to do for supercapacitors, for instance, it becomes more difficult. And people have been playing around with standard Ewald sums for 2D partially periodic systems, and it's a mess because it's very slowly convergent, and you have to hit the right parameter range. And so what the first idea was, just use plainly 3-dimensional periodicity, and just don't care about that you have these unwanted interactions, which are now here in the Z direction. This is, of course, not very nice, and therefore not very good. So there are a bunch of periodic solvers. I don't want to really go into I mean, here's this P2 NFFT. It's a non-equidistant NFFT. It's kind of difficult. The easiest correction you can do is the so-called Yeh-Berkowitz correction. There they used a simple effect, which says I still gonna use the 3-dimensional periodic sum, which I know from Ewald, but what they did is they added a dipolar term, which is this dipole term, which we were talking about in the Ewald sum, but in a particular form, namely that you just add the Z component of the dipole term. And they showed that this actually reduces the artifacts by quite some amount. And the reason where it comes from is actually that the dipolar term, I told you before, says something about the summation order in which you sum up these interactions. And the change in summation order with this particular dipole term is such that you first do the summation in the planar geometry. You sum up infinitely in planar geometry, and only after you've done that, you sum up in the lateral direction in Z, and that reduces the errors already considerably, but you still make errors, of course, because you still have these interactions of the periodicities. So therefore, at some point, we looked at this problem about 20 years ago, and we came up with this, what's called the ELC method. It's called for electrostatic layer correction. I won't go into details, but this is actually an exact method. So therefore, there is no artifact remaining, but you can actually show how you can sum up the interactions in this direction which you do not would like to have. And then once you have that, you can just subtract that from the standard Ewald sum. And what remains is just the planar interactions. And this is an exact term, but as always in Coulomb sums, if you make it exact, it is infinite amount of work. And so it's again convergent sums, which you can cut off at certain point in order to have a certain error. This is also all under error control. So we have formulas by which we can say you have to cut off here, and then you remain this and this error. You still need a separation from the slabs. I mean, like in this Yeh-Berkowitz one, but the separation can be made much smaller. And so it's typically 2 to 4 times faster than plain Yeh-Berkowitz. Plus you have full error control, plus the artifacts near the interface are much more diminished, because Yeh-Berkowitz has the problem that especially at the interfaces, this is where the error becomes largest. It's an non-homogeneous error. Now, I was talking a little bit about ScaFaCoS. ScaFaCoS library was a scalable, fast Coulomb solver library. I mean, this is where the abbreviation comes from. Was developed with lots of colleagues 10 years ago by us, and it contains basically 11 methods of implementing the periodic Coulomb sum. And you can see these are all names. Direct, of course. Pepsi is I mean, let's see. This is no, this one is a fast multiple method, which is normally scaling like n, but has a large prefactor. And we were interested, how do they compare in terms of accuracy and speed? And for reference, you can have a look at this paper from 10 years ago. And the outcome was that basically P3M, this P2NFFT, which is more or less the same as P3M, just in a different way, and this fast multiple method are the ones which are more or less performing equally well, and showed also the same sort of scaling behavior. But we learned when we did this comparison with all these experts on their own different methods is that you should never worry about factors of 2 or 3, because that really depends on the artistic capabilities of the person who tunes the algorithm. Whenever we said, okay, we look at this system and we want to see who is fastest. I mean, if you spend 2 weeks, you make your thing twice as fast, and then you spend 5 weeks on the other method and you can still beat him, because there are always things you can optimize, but you shouldn't worry about it. I mean, for me, the outcome was that P3M, we know how to work with it. We know how to control it. So I work with it, because I don't care about this ON scaling versus ON log n scaling. It will not show up in my systems, because you have to go probably to billions of charges in order to see it. I don't know, I might overestimate, but we haven't seen anything with millions of charges. So go an order higher and you're over the billion. Now, dipolar interactions can also be handled. I won't go into that. Let's go now to dielectric interfaces and look where does this matter. Because in water systems, you have a dielectric constant throughout, which is within this implicit solvent assumption. You take water to be of epsilon r equal to 80. But if you now have an interface, so that means you have water near a solid state block, then of course water has a dielectric constant of 80. The solid state interface might have, I don't know, 2, 3, 4, depends how flexible the charges in there. And that leads to something, to a dielectric interface. Now, as I said already, for these coarse-grained systems, you have epsilon around and maybe 2 in here. So what does it lead to? Well, it leads to a dielectric boundary force, which you know from electrostatics, because if you come from a high dielectric media and you have a charge, it will induce, or if you solve the electrostatic problem, you will see that you have a repulsive boundary force, because what you do is you induce a charge on the other side. You can solve this with this method of image charges, and that charge on the other side, which have the same sign, you would have a repulsive dielectric boundary force. And therefore, this is something you would in principle have to take into account if you're interested in looking at charges near dielectric interfaces. Now, the question is how to compute this efficiently. And there are these two methods. Either use image charge, so this is what you probably have learned at some point in your electrostatics lectures. I mean, how to solve the potential in front of a dielectric boundary, or you use what's called induced charges. And there are two methods which you can more or less implement. We have in ESPResSo basically two ways of doing this. The one is this IC MMM2D, which is very slow, but can do it in this ELC-IC, which is basically, I mean, these 2Ds come now about because we again are in partially periodic geometries. Remember, we're no longer in 3D. This is an interface. So that means we have 2D periodic boundary conditions, and in this direction, it's non-periodic. It's very, very fast for planar interfaces, but you might not be always interested in planar interfaces, because sometimes you have curved interfaces. You might have any complicated interface you might imagine in terms of these porous electrode materials. Celine or Mathieu will probably talk about that. So therefore, how do you deal with those interfaces? And here we developed what's called the ICC star algorithm. It's basically based again on continuum physics. What you do is you would like to fulfill boundary conditions for the normal components of the electric field, because you know from electrostatics that in the perpendicular direction you should have a jump of the electric field given by this equation. This can be fulfilled by introducing a charge density of that size. And in order to implement that this boundary condition is true in the presence of a dielectric interface, you do a discretization of the surface boundary elements. So you say, okay, if I have some arbitrary curved surface, I will just chop it up into little boundary elements. On each boundary element, I put a charge, and this charge should have a value. I mean, it should introduce a charge density exactly of that sort. So how do I get this amount of charge? Well, I have to solve it by an iterative scheme. And this epsilon can be obtained, I mean, not the epsilon, the electric field, which you need in order to compute this jump on the boundary, can be obtained by any Coulomb solver. And this is why we call this ICC star. Star stands for you can use whatever. And of course, you want to use, let's say, the fastest. And for us, this is always the P3M. So we normally use it with P3M. And the periodic boundary conditions you can automatically fulfill in case you need them. If you don't need them, well, then use a solver which doesn't have any periodic boundary conditions, which also exist. And it's pretty fast. So it depends, of course, on the level of discretization. So you have to add these additional charges on each of your boundary element, but that allows you to compute induced charges now on all the boundaries. Now, let's come now to constant potential algorithms. Let me see. Yep. Because I was saying now, in doing supercapacitors, for instance, what you do is you would like to solve now the distribution of charges in front of a constant potential surface. So what's a constant potential surface is where the potential is constant, but normally it's a metal. I mean, this happens in metallic systems because the electrons are free to move and they have a constant potential throughout. And therefore, if you think in terms of dielectric interfaces, why not just choose as my dielectric interface a metal system? So where actually my epsilon on the side where I am looking at is infinity. And that really produces, again, a constant potential surface. And therefore, we can, in principle, with all our methods which we have developed for dielectric interfaces with this MMM2D, ELC, and ICC, they also work for constant potential via setting this epsilon r to infinity. Now, for details, you can look in this algorithm, because there are some things which you have to remember, that these algorithms model a structureless continuum metal surface. That means there are no other electrode properties included. It's the continuum idea of having a perfect metal wall with no corrugation. The electrons are free to move anywhere. There's basically perfect screening in your electrode. Now, there's an alternative but physically different method, which is known under the name constant potential method, where you put actually Gaussians on your electron atoms and you give them a certain charge distribution with alpha. And I mean, there was something which was only recently became clear to me, because I always thought that must be somehow the same method. But in principle, it's not the same method, because you do something physically to your electrode. You prescribe a certain distribution, polarizability, let's say, of your atoms to the electrode atoms. And this was done already a long time ago by Siegmund Sprigg, and Madden and Reed did this. And this is what Mathieu has been using for a long time. And there are basically two implementations out there, this metal walls and this electrodes, and Mathieu will probably tell us a little bit about it. But the point is that this width of the Gaussian is related somehow to the hardness of your electrons. And so physically, it's a different method. And so it will also produce potentially different results from the method which you're using here on top. And with this, I'm at the end of, no, not yet, not yet. Just a second. So I come to my conclusions, which I just want to get rid of. So there exists plenty of Coulomb algorithms. You should choose the one with a decent scaling or small prefactor, and this depends normally on the number of charges you're using. I would prefer to use a method with full error control, and preferably use a method you know best, because there are always some parameters which you have to tune. And so you have to have some knowledge about the method. Otherwise, of course, there are some packages like ours which tune the parameters for you. There's Gromex, which also does some magic for you. But if you don't know what it does, I would always feel a little bit uneasy. So you should at least try to look what's happening. ESPResSo offers many other methods, like the one with ScaFaCoS. But for us, normally the standard horse is P3M for the bulk systems, for the 3D periodicity, ELC, and ELC normally for 2D systems. If you're interested in dielectric interfaces or constant potentials, then we use ICC star or ELC.